Hello everyone, this is Jay from
BTYT Tech Library.
Today we are going to solve on Halloween night. You are going to hand out candy to youngsters with the following rules. Each child must have at least one candy. Children with a higher rating get more candies than their neighbors. What is the minimum number of candies you need to distribute? We can create another array as a candy bucket with an initial value of 1 candy per child. Then, we compare the head of the rating array with the next value to the end of the array to see which child got more candy than the child behind. This approach seems working, but not good as enough, because the term in conditions neighbors try to trip you up. What about the child standing in front? What's the thing behind you? How many candies do you need to give that child? The thing is, the amount of candy to give each child isn't determined until you can scan all the ratings in the array. So following the first step of algorithmic problem solving, get it done first. We need to do 3 loops to solve the problem. First loop for comparing the assigned rating of the child to the right side. Second backward loop for comparing the assigned rating of the child to the left side. Third loop for moderating the candy counts to make sure the children assigned a higher rating get more candy than the others who are standing from there either to the left or right side. Okay, now get down to the second step of algorithmic problem solving. Optimize the solution. The reason we need the third loop is that there is a case where the candy to the child assigned with the highest rating is wrongly given, because during the second loop, the calculated number of given candy compared with the child to the right side override the candy count calculated by comparing with the child to the left side. How about handling the third loop's task in the second loop? Calculating the amount of candy to give by comparing the rating with the child to the right, then concluding the proper amount of the candy with already determined from the former loop. With this, we can decrease the number of scans in the array from 3 to 2. Good. Let's go to the next step of algorithmic problem solving. Can we do better? In the first place, the reason we need to loop the whole array twice is that on the first iteration, we can't tell how many candies we need to give these children until we scan the rating array from head to tail. Really? Is that true? How about a half? If we know the array size and one point in the array, then we can also find out its antipodal point in the array. I mean, if we can pick one element some distance from the head, in the same manner, we can pick one element from the same distance from the tail. 2 steps forward from the head, 2 steps backward from the tail. Symmetry. Let's solve this way. Starting from the array's both end, calculate the amount of candy to give by comparing with the rating of the corresponding child and the child standing in front pairs until both scans meet in the middle. After they cross each other in the middle point, we are going to conclude the proper amount of candy between already determined from the opposite flow and our calculations. In that way, we can solve this problem with only one loop. Let's code it up. Let's create a candy bucket filled with one candy for one child. And check the half point of the array. Through the entire array, on half, we will give extra candy based on the rating. The other half, we will give extra candy based on the rating and the candy children already have. And return total candy count in the bucket. Let's run the code. Hey, I couldn't help but stress that there is a hidden step in algorithmic problem solving. Have some fun! Actually, we can solve this problem by a one-pass loop with constant memory usage. And we can use the toy that most of the children love about, even more than candy or chocolate. Mathematics. Wait, what? Let's visualize our candy distribution. Obviously, there are rules for handing out candy. Each child must have at least one candy. Children with higher rating get more candies than their neighbors. The thing is, even though the gap between two ratings is greater than 1, the candy to extra give is 1 will be enough. Are you seeing this? If we draw a graph of candy distribution, we can find the triangles in it. Actually, this graph is made up of right triangles, which have a positive or negative slope and a flat line. These figures remind us of the triangular number and its formula. So we have two types of right triangle. One is a triangle with a positive slope. We can apply the formula as it is. However, all the children initially get one candy, since extra candies are given in addition to the initial distribution, so we need to add those. The rectangular section under the triangle. What about the triangle with a negative slope? It is also the right triangle. So we can apply the triangular number formula. The difference is this time, following the negative slope. Running down with the down steps, children lose their extra candies. So we don't need to add the candy initially given. We are almost done. There are a few things we need to handle. One is handling the condition of children with a higher rating get more candies than their neighbors. If we have two different types of right triangles that meet at the different heights, we will fill in the gaps with extra candy. The other is handling the same rating. If you are see flat line, just give one candy. Finally, we need to start candy distribution by giving one candy to the child in the front row. So we are going to accumulate the total candy count.
Starting from 1.
Now we've transformed the problem of counting the minimum total number of candies into a slightly modified triangular number calculation. Let's code it up. In this case, we don't need a separate array to count the candies. We need only 3 variables. Up steps of the positive slope, down steps of the negative slope, and amount of candy. And let's implement the helper local functions. One is the terminal function, which is the formula for the nth triangular number. The other is calculate both type of triangles. If it is the right triangle with a positive slope, we need to do an extra calculation about the initial candies. If it is the right triangle with a negative slope, we need to fill the gap of the loss of candy that should have been given. Let's start a distribution with only one pass loop. There are 3 cases of the graph pattern. Right triangle with positive slope, right triangle with negative slope, and flat line. We are going to update the candy count at 3 points. One is when a right triangle with a positive slope starts. Another is when it enters a flat line. The last one is after the loop is completed. Let's run the code. That's it. If you liked the video, please like and subscribe and leave the candy or chocolate emoji in the comment section. Because trick or treat.